Hi again, I'm Yunus Şahin from CogIST. It's been a long time since we didn't meet for a cognitive webinar. Today at 17 Cognitive Webinar, Dr. Cameron Buckner from University of Florida is here with us. He received his PhD at University of Indiana on computational models of reasoning in human and animal minds. He has been carrying research at the intersection of artificial intelligence, cognitive science, and philosophy. He develops an empirically informed approach to the philosophical problems in these areas, in these fields. And today we will listen to his talk with the title Language Models as Models of Human Reasoning. Once again, Dr. Cameron Buckner, thank you for accepting our invitation and for this talk. So please go ahead.
Okay, I'm going to go ahead and share my slides. You see everything okay?
Yes.
Okay, so thank you for the invitation. I'll jump right into it because, as usual, I have way too much to say. I'm probably not going to go through all my slides, but I'll leave some of them as a stub. I'll try to check in at the 40-minute mark to see if you want me to keep going or you'd rather open it to Q&A. Um, I'm going to begin by giving a little background on my book and what I've been working on generally over the last 5 years. But the main topic today is to consider recent advances in large language models like GPT-4, o1, o3, and DeepSeek to evaluate their suitability as models of human reasoning. And to do that, I'm going to go through a few different ways that they could be relevant to understanding human reasoning. So, for example, we might look at their performance on tests of reasoning, the same kinds of tests that we would give humans. We might look at the distinctive kinds of mistakes they make on reasoning tests. These are all sort of increasing levels of cognitive theoretic sophistication as we go down the list. The third twig, and this is getting very interesting just over the last few months, is to scrutinize some inner chain of thoughts that some of the newer models like O1 and O3 and DeepSeek produce in solving problems. And then this is probably what I'll check in to see if you want me to keep going. A lot of my recent research, also with Raphael Millier, has focused on mechanistic interpretability techniques to try to probe the inner workings of these systems and understand their causal organization, even to a degree that wouldn't be possible in human brains. And I think that's actually the most promising approach to forecast, but I'm going to lead up to it by considering insufficiencies in the previous approaches. And I also will mention there's a whole different set of approaches that especially would be interesting to sort of digital humanities type scholars, where we just consider these as kind of models of textual culture and so indirect evidence of the structure of human reasoning. But I won't really get to that other than to just gesture at it. Okay, so to give you a little bit of framing of my book project, in case anybody wants to look a bit deeper and get into that, you might be wondering, okay, I realize a lot has happened over the last 5 or 10 years in machine learning, in particular in deep learning approaches to AI, which are these very deep artificial neural networks that have produced all kinds of really impressive breakthroughs that you've no doubt heard about in the popular press over the last few years. A lot of skeptics, even within cognitive psychology, have pushed back against deep learning and said, this is just neo-behaviorism. So this is a picture of American psychologist B.F. Skinner, who led this kind of radical behaviorist movement in American psychology in the middle of the last century. And the idea was you can't even theorize about inner cognitive states and sophisticated higher cognitive type problem solving capacities. You should just look at sort of patterns of input output statistics at the periphery of the organism. And my book is just sort of around a resounding no. This is not the right way to understand what's happening with deep learning. The victories there are not at all to be understood as a kind of neo-behaviorist approach, right? So this is not just Skinner. And I try to press that point home in the book with 400 pages of examples of deep learning research that doesn't fit this behaviorist mold. And I go through lots of different architectures from a kind of philosophically informed perspective, especially drawing upon empiricist philosophy of mind, where the idea is Skinner and other behaviorists like Watson were a kind of outlier in the sort of empiricist camp. They were the most radical and oversimplified versions of empiricism. And it's not the kind of empiricism you would find in philosophers like Locke or Hume or most contemporary theorists that say they're empiricists today in either artificial intelligence or psychology. So check out the book if you want to hear all the details of those arguments and case studies. The general framing for the book, right, is just to ask, what is the origin of abstract knowledge? How do we come to have abstract knowledge? That's a scientific question in the case of human and animal cognition, and it's kind of an engineering question in the case of machine learning, right? Because the thought is we have one set of systems that seem to be able to learn abstract knowledge reliably, especially humans. So, as a first start, we might want to look at how we do it as a guide to how to build the right AI systems. In turn, success in machine learning in acquiring abstract knowledge in particular ways might provide more evidence that this is the way humans actually do it. And I talk a lot about some simple examples that have been frequently discussed both in the history of philosophy and the history of psychology, like how is it that we come to have simple abstract ideas like the idea of a triangle in general, where it's not a particular triangle, but rather something that somehow encompasses all of the idiosyncratic variation you might see in particular triangle exemplars. Now, the question is, in understanding the successes of deep learning, you can build a really good triangle recognizing program with a deep convolutional neural network. And it's trained, it seems, entirely from direct interaction with problem data, say from high dimensional digital photos. In what sense should we understand this as a kind of victory of the empiricist perspective, which has all along said this abstract knowledge comes from sensory experience rather than being kind of innately built within us? Now, if you ask the nativists, these are people who think that innate knowledge is responsible for our understanding of abstract concepts and categories. They have a very impoverished idea of what the empiricists can appeal to here, right? So the empiricist perspective is often associated with this blank slate metaphor, right? All the way back, way before even Locke to Aquinas, this was a metaphor for the wax tablets that Greek academies used to take notes, right? Where the idea is you would heat them up and they would reset between each lecture and you could take notes again. And this was supposed to be a metaphor for the mind of the child when they, are released into the world and they then start acquiring patterns from exposure to sensory experience. Now, Steven Pinker and other nativists interpret this metaphor literally, where the idea is like there's literally nothing inside the mind. It's just literally like a sleeve of baked stone. So they can't learn anything. This is just a silly perspective. Gary Marcus, who was, a student of and associated with Pinker, has even tried to put a sort of formal garb on this construal of empiricism. You could think of cognition as a function over four variables. They say A, R, K, and E, where A is innate algorithms, R is innate representational formats, K is innate knowledge, and E is experience. And they say a true blank slate would set K and R to zero, A to some extremely minimal value, and leave the rest to experience. And he says this is essentially the view Locke articulated when he said all ideas come from sensation or reflection. And when I read this bit from Marcus, this is when I said, oh my gosh, this is so wrong. I have to write a whole book saying how wrong this is. Because if you read even the next few pages of Locke, he talks about all kinds of things that don't fit this mold of empiricism. He talks about attention. He talks about processes of abstraction. He talks about memory and imagination. And so that's really what's missing from this straw man picture that the book tries to illustrate is really present in a lot of deep learning research. In particular, empiricists, moderate empiricists, which is, I think, the kind of empiricism that should be attributed to deep learning, can have a cognitive architecture, right? It just needs to be a cognitive architecture of a particular sort, a non-nativist sort. So this is a straw man view of empiricism. Don't believe it and don't let people tell you this is what they're doing. So what's missing is a kind of basic empiricist faculty architecture, and this is very common in some form or another in all of the major empiricists. In the book, the way it's structured is each chapter is structured around a particular faculty from an empiricist faculty architecture, like perception, imagination, attention, or memory. There could be lots of others. These are the ones I focused on. And each chapter has a kind of empiricist of the week format, where I focus on a particularly, I think, promising view of what that faculty is from a historical empiricist philosopher, and then show how a lot of their ideas have already been realized in existing deep learning research. And then there's still maybe some more enticing ideas like aspirational goals to hit in other research. The general argument of the book is that the success of deep learning research is a vindication of this kind of moderate empiricism. It should increase our plausibility in thinking that this is the right approach to the human intelligence and the human's ability to acquire abstract knowledge. Now, if that's a success, especially in the more basic faculties like perception, imagination, and memory, you might wonder, oh, can we really go for the big, higher cognitive faculties like reasoning? Okay, and that's a goal I don't tackle in the book, but I'm tackling in my more recent research and in this talk, right? Because you might think reasoning is just a matter of kind of bootstrapping all these other faculties together in a sufficiently sophisticated way for advanced problem solving, planning, and so on. So I call this the new empiricist dogma. If you've read your Quine, you know that's an allusion to the two dogmas of empiricism from Quine. I think this is the new dogma, but this here, if you want computer scientists to take you seriously, you have to have a good acronym. So this is Domain General Modular Architecture is what dogma stands for here. Okay, so let's now talk about the most recent research in LLMs and whether these things can now be treated as models of human reasoning, because at least it seems apparently like something that should be investigated as plausible, because if any of you have interacted with, say, GPT-4 or Claude Opus recently, it sure looks like they can do some pretty sophisticated stuff that we might, at least on a cursory inspection, call reasoning. So these are large language models, as you probably know. They're massive pre-trained versions of a kind of architecture called a transformer. I'll go very briefly into what that means in a second. They have billions or trillions of parameters. They're trained on lots of energy, at least until DeepSeek. That remains a little controversial. I'm not really going to get into how much energy it took to train DeepSeek or not. But they're pre-trained for next token prediction on very large data sets, huge swaths of the whole internet of digitized text, in order to get pretty good at constructing the kinds of sentences that humans would produce in similar circumstances. And then there all kinds of other things happens. They're further fine-tuned. I can go into the further other methods of training these models if anybody's curious later on. The long and short of it is it's a lot of stuff, and it's a lot more than just the simple construals of how the training works you might have heard before. So like I said, this includes very popular chatbots we have access to today, like the GPT series, Claude, Llama, open source options, also Gemini, and so on. Now, the basic way these models represent meaning, if we're evaluating them as candidates for abstract knowledge, is with word vectors. Okay, so I'm just going to give you a real quick crash course on the idea of vector space semantics and how, with a very large artificial neural network, you might represent something like meaning at all. So the idea here is there are vectors of activation values in very large neural networks. You've got billions of nodes, and some of those nodes are active in certain ways at certain times. And those activation patterns are the vectors that might be candidates for representing meanings. It's actually clusters of vectors, but I can get into that later. But you can see really quickly how, with, say, a simple ambiguity task in a sentence, how just moving vectors around in activation space might solve some semantic problems, right? So suppose from free training, you've gotten a series of vectors clustered over here that have to do with, say, financial institutions, and you've got a cluster of vectors over here that have something to do with, let's say, rivers, and estuaries and so on. And then you read this sentence. Maria was fishing on a sunny day. The sun was high in the sky and things were peaceful. Suddenly, that peace was shattered when her cell phone rang. In order to answer it, she stepped away from the bank. Now, bank in English, I hope this carries over to Turkish, is an ambiguous word. Okay, it could mean riverbank, which is the side of a river, or it could mean financial institution, which is where you go to, deposit your money and checks and so on. So it's an ambiguous word. And the idea is if you had the ability to dynamically move the vector representation for bank around in vector space on the basis of the context in which the word occurs, then you would have the ability to disambiguate it, right? So maybe the kind of intrinsic or naive vector space representation for the word bank is kind of equidistant between these two possible meanings. But you can use these context cues to move that vector around. You can say in this particular context, I should move the vector for bank closer to riverbank because Maria was fishing. It's unlikely she was fishing in a financial institution, right? So that's one way you see just by moving vectors around. The idea here is that vector distance is a kind of proxy for meaning, semantic similarity and relevance. You can solve some semantic problems like ambiguity resolution. Now, what transformers do, the kind of architecture behind large language models, they just do that on a very, very grand scale. Okay, that's what the self-attention mechanism allows these things to do, is much, much more sophisticated, flexible, context sensitive, dynamic moving around of the meanings of particular vectors in the particular context in which they occur, right? So this is very far, if you've had some earlier exposure to connectionism, what's going on here is much more subtle and sophisticated and powerful, unsurprisingly, based on what these models can do today. In particular, in transformers, each token or word, it's easier to think about representation, is actually represented with a series of three vectors in self-attention called the query, key, and value vectors. Okay, so the key for each word or token represents the intrinsic meaning of that token across all contexts, right? So that's like undisambiguated bank. The query represents the meaning of the word's context in the current context or prompt, right? And then the value vector, that's the one you really want, is the way the vector for that token has then to be moved around to get a better grasp of its meaning in the particular context in which it occurs, right? Now, many self-attention heads are operating in parallel and in a deep hierarchy in all of these systems, right? So you can represent many different aspects of the same word's meaning in parallel, right? One could track the way it's modified by an adjective, for example. One could track subject-verb disagreement. One could track the member of a clause. One could track anaphoric resolution from a previous sentence, right? You can have lots of different heads doing lots of different jobs with the same word in the same context. Now, again, moving vectors around in this way, we've empirically discovered, allows their context to transform the vector representations to accommodate a wide range of long-distance syntactic, semantic, and pragmatic phenomena. So you can solve, like I said, ambiguity, anaphor, grammatical relationships, sequential patterns, and so on. You can even, and this was very surprising, learn entirely new patterns on the fly from so-called few shots in the prompt, right? That it's never seen anywhere in its training set. So it's not 1980s connectionism, much more sophisticated than that. What we really got is this self-attention operation, which dynamically moving around lots of vectors. There's lots of those in parallel at the same time, interacting with each other at multiple hierarchical levels of processing. And so if you want to say, what is the transformer's representation of the meaning of this word? It's really this giant thing. And you can use lots of visualizations to try to figure out what it means, where this is a visualization of the weight that different attention heads and different layers of the network place on particular words. So what's the representation of the meaning of this word? It's this whole thing I've just showed you, right? And this is for a very small, simple transformer. Very daunting, right, to interpret what's going on. But in particular cases, you can get a pretty good gist. So here, for example, is a kind of visualization of how an anaphor resolution might work with query, key, and value. Okay, so suppose you get one of Asimov's law of robotics. A robot must obey the orders given it. It here is an anaphor, right? So it's sort of intrinsic naive vector, meaning should be like radically underdetermined. It could mean all kinds of different nouns, and you have to look at the context. So what you see here, and this is from a trained up query value, is that this query vector is placing a lot of modified the value of this word it in this particular context, right? So you can see how you could get this anaphor resolution type problem, a kind of difficult problem for understanding sentences with key query and value vectors. There is a position paper by Goyal and Bengio that argues adding this mechanism transforms neural networks from machines that are processing individual vectors to machines that are processing sets, in particular sets of key value pairs, and that this implements a simple version of variable binding. It's a kind of attenuated, limited version of variable binding, but it's something much more sophisticated than you would have seen in earlier neural network architectures. There's a lot of other cool results, especially from Anthropic, has done a lot of very careful mechanistic work. Another thing you find in these networks is there's a kind of mathematical abstraction through the many layers of self-attention heads called the residual stream. And networks that are trained up can treat this residual stream as a kind of read-write memory, where an earlier head in the layer can print some memory, some information to this particular location in the residual stream, and a later head can be trained to pick up whatever that earlier head is passing it. And this might be responsible in part for some of the on-the-fly learning of entirely new patterns and rules that these networks display in particular contexts, right? You know, in some sense, that pattern has never appeared in their training set, and yet they can pick it up just like a human with from just a couple examples and seem to apply it consistently. So if you're curious about that, I urge you to look at some of that research. These are called induction heads that get this coordination in research by Anthropic, but I can't fully go into the details here. So let's now talk. So lots of sophisticated stuff going on in these models. Looks like it's doing a limited version of variable binding. You might think that putting all that together, you might be able to get some reasoning abilities that are much more flexible and adaptive than previous neural network architectures were able to muster. So how would you measure that, right? Suppose we were treating that as an empirically live option. How would we decide whether it's true or not? Well, one obvious thing to do, and a thing all the major tech companies have already done, is just apply existence performance tests that we use to evaluate human reasoning, okay? Like the graduate record exam, the GRE, or the SAT. These are tests used to rank candidates for undergrad or graduate admissions in the US. You can give them IQ tests. There's all kinds of different IQ tests out there to give them, and so on. Now, if you do that, you find that, unsurprisingly, earlier versions of GPT, for example, were starting to approach human level on lots of different aptitude tests. And GPT-4 is in many cases exceeding average human performance, in some case, getting up to 90th percentile on some of the most difficult types of aptitude tests. So you might say, oh, wow, if we were ranking these things just like humans, it looks like they would be in the top 10 or 20 percentile of human applicants for graduate school. More evidence to that effect. And you can find all kinds of this evidence out there if you do a quick internet search. There's even other more sophisticated things we could do. So suppose you were a little bit skeptical of some of these aptitude tests and what they could really tell us. You can test anything you want. And so other big projects, this is from the Big Bench project. When I teach this, I call this the paper with a bazillion authors, because everybody who contributed tests to this suite got to be on the paper. So this keeps going for quite some time. But what they get from the result is like a big test suite that you can go download and apply to your model that you've built and see how well it does. And they can try to replicate everything you could think about, any kinds of cognitive tests they get from anywhere in cognitive psychology or animal cognition, and just see how models do. And unsurprisingly, there's a reasoning section, right, which contains a whole bunch of particular reasoning problems that are specifically designed to assess reasoning ability. And again, as you find, as these models get bigger and have bigger training sets, they do better and better on reasoning tests. Okay. So in particular, when you add chain of thought prompting, and I'm going to talk about this more later, this is the innovation with GPT-4 o1, o3, and DeepSeek. You start to get much, much better performance on reasoning tests. And that's indeed how they market these tools. They say now these models can do reasoning. Now, let me give you a very general, philosophically august reason to be suspicious of pure performance tests as showing you that these models reason. I like to appeal to this thought experiment from the 80s by philosopher Ned Block we now call it the Blockhead thought experiment. And the thought experiment goes like this. Imagine any time-limited conversation you could have with an AI. There are a finite number of responses and counter responses that could be made. This is definitely true. And if you try to come up with a completely novel test for these systems and then Google it on the internet, you will often find humans are not as creative even as we like to think we are. It's very difficult to come up with a problem that somebody else hasn't already thought of before and put somewhere on the internet. But suppose you then had a very large a very large government grant, and you could hire all the world experts and you just get them to, manually program the best answers to all of these questions in some very large database. Okay. And then the system does nothing more than memorize all those responses and regurgitate them every time somebody asks that question to the system, right? The resulting system, it would pass the classic Turing test, right? There's no way you could tell the difference between this system and the smartest person in the world because you've hired all the smartest people in the world to say what they would say for this system. But intuitively, it's not intelligent, right? I would kind of say this is like the student that stole the answer key to the exam and gives the same answers as the student who studied hard and is kind of like generating their answers by processing the questions you give them. Intuitively, while the theft-based responses might be, an intelligent example of larceny, it doesn't demonstrate intelligence in the skills it was designed to assess, right? And I hope you share that intuition. Sometimes people push back, but it seems like an obvious intuition to me. Um, Now, what's interesting to me, this is supposed to show that no purely behavioral test is going to be adequate for demonstrating intelligence, if this is a possibility. What's interesting to me is that a blockhead style memorization is actually a live empirical option based on what we know of how deep neural networks work. In particular, there were these studies by Zhang et al. Called "We Still Need a Better Approach to Generalization in Deep Learning," that showed that because of their hierarchical structure, it's a technical result I can explain in the Q&A if anybody wants. You can give them tens of millions of very complex, randomly labeled data points, and it can get basically zero test error on those data points. It can, in other words, has a huge memory capacity, like a kind of memory savant. It can simply memorize the right answer on tens of millions of highly complex data sets where you know there's in some sense no abstract principles that it could master to figure out what the right relationship is between the data points and the correct labels, right? And this kind of ports over to any deep hierarchical neural network. I mean, there's also been court cases, right, against, say, OpenAI, where New York Times, for example, shows you can get it to kind of regurgitate large sections of articles that were published in their newspaper, and people generally can't do that. So if we're comparing humans and animals on these tests, it seems like it's not a fair comparison because humans don't have that, by and large, astounding memory capacity. Maybe some savants do, but let's set that aside. Um, right now, consider that the training sets of these things are internet scale and largely proprietary. Unless you work at OpenAI, you don't even really know what's in their full training set. So, so-called contamination of their data is a live option to explain any particular result that you get. And you know they've trained the system on tons of sample GRE and SAT tests, and probably they have algorithms to generate a whole bunch of potential questions that could be on them. Um, there are attempts to make these purely aptitude type tests much better, especially based on a kind of psychometric tradition. Francois Chollet, who works at Google, is maybe one of the most prominent researchers attempting to make these tests better. And what he tries to do is say, let's focus not just on particular aptitude in knowledge domains that could be readily available on the internet. Let's rather look for skill acquisition efficiency. And let's try to make some super abstract problems that are only testing very, very abstract forms of knowledge and on problem types that we have very good reason to believe couldn't possibly be in their data sets, right? And the idea is that this might control for some of the blockhead style worries, which Chollet is very aware of conceptually and has a kind of philosophically sophisticated approach to. But if you look at the tests that you get at the end of this, they're very ecologically invalid. I have this worry, this sort of like, what are we even testing at this point? How would a human do on these tests? And if a human couldn't pass these tests, if you're trying to guess what you're supposed to do here, it actually takes quite some time. And imagine now doing this in a non-linguistic setting where you don't even really know what the task is that you're being asked to perform. It's just a kind of completion task. There's also a book I'd urge if you're curious about the psychometric tradition here. Jose Hernandez Arroyo has taken this approach very far and is fully aware of kind of worries about the tradition. If you want to get deeper. In general, I don't think that Chollet-style revisions to the psychometric approach are adequate to address memorization worries that we might have here. And they really don't tell us the thing that I think most cognitive scientists and certainly most philosophers are interested in when they want to know whether these systems are reasoning, which is, are they sensitive in a sophisticated kind of internal transition way to the internal representations of the problem that they're solving? And are they performing particular kind of algorithmic like steps to transform the input to the output? Are their transitions sensitive to the evidence in the right way? Maybe truth preserving or credence preserving. Is internal confidence really tracking anything like, degree of belief, right? The kinds of things that cognitive scientists study when they try to understand internal processes of reasoning. It's still a purely performance-based metric, in other words. Now, slightly more sophisticated, and there's another approach that's based on a little bit of dissatisfaction with the Chollet and psychometric style approach, is maybe we should look not for when these systems get things right, but do they produce the same types of idiosyncratic mistakes that humans and animals produce when they're given similar problems? Because you might think there's a kind of many to one problem when it comes to success, right? If what these systems are trained on is success, there could be many, many different algorithms that will get you successful performance on a task. And there's even formal results that show this, right? But mistakes might be a little bit more diagnostic, right? All of these different things might show different patterns of error. And so if you find a system that has different subtle idiosyncratic patterns of error, you might think that's better evidence that it's solving the problems in the way that we are, as opposed to in a very different way, right? This is an old idea in connectionist research. If you look back in the 80s in the PDP Bible, with McClellan and O'Reilly, McClellan and Rummelhart, you can find them making this argument in the case of, really old school language models that they say do overgeneralization errors in English conjugation of verbs, right? So, children, when they're learning to conjugate verbs, they might think break goes to broked, but really it's an irregular verb, right? Which you have to kind of learn by rote. The past tense is broke. And they had connectionist models that reproduced that intermediate training error that classical models didn't. And so they argued that was a good reason to believe these were models that were learning verb conjugation in the way that human children do. And so we might ask, do large language models recapitulate human errors spontaneously in this way? There's been a lot of interest in the past for vision models, right? So these are models that are meant to classify, say, high dimensional images in the same way that humans do. People have asked, cognitive scientists have asked, for example, do they have a shape bias as opposed to, say, a texture bias or a color bias? It seems like humans and animals have a shape bias. They tend to group objects together into categories based on shape rather than color or texture. And some deep convolutional neural networks appear to have a texture or a color bias instead. And so you might say, oh, that looks like they're not doing the same intermediate processes that we are. For example, when you see this picture, do you think that's a cat or an elephant? Most people will say cat, and most deep convolutional neural networks will say elephant because it's an elephant texture. We could do versions of that on reasoning tasks here, right? To see, do they have the same patterns of error that we do that would indicate the same kind of intermediate biases or representations, or do they have different ones? Um, so if we look, do these systems reproduce human errors? They do in many cases, but it's not that surprising because they were trained on human generated data sets, right? Which are full of human errors. So, people, for example, if you know the heuristics and biases tradition from Kahneman and Tversky, some people looked at, do they make the same mistakes on the Linda problem that humans do, right? To remind you, here's the Linda problem. You say Linda's 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice and also participated in anti-nuclear demonstrations. And then you ask which alternative is more probable for Linda's future profession. She's a bank teller or she's a bank teller and active in the feminist movement. Most humans choose the latter option. This is the so-called conjunction fallacy in probability terms, because if these are conjunctive events, it's impossible that the conjunction is more likely than either of the one events in isolation, right? Um, and in fact, you find versions of the conjunctive fallacy are committed by large language models that are trained on human data. So you might say, look like they're creating the same mistakes. But again, I think that's simplistic reasoning because there's tons of examples of conjunction fallacies from human data in the textual data sets, right? Um, One thing you might look for is, do they make a lot of mistakes that humans don't make when they're tested on statistically unlikely inputs that probably aren't in the data set, right? Um, so one example, this is just a position paper that makes this case of looking for distinctive mistakes if anybody wants to get further into the idea. Um, Give you a little background on this paper. There was a study from DeepMind not too long ago called Machine Theory of Mind. And they did this thing also where they suggested if we test we test these deep learning agents on
Okay, I dropped out, but uh, I think the professor also. Okay, you are muted.
Am I back? Sorry, I warned Eunice earlier. My internet is being worked on today, but let me try to get back to where I was. It's like I got to reshare my screen. Is that right?
Yes.
All right. Sorry. Give me a second. I hope that doesn't happen again. All right. We good?
Yeah, great.
All right, I'll try to get back in the groove. Right. So, deep learning models seem to pass human versions of theory of mind false belief tests, but we might wonder, do they pass these modifications? Right. Everybody gets the context of this task. You can see there's no chocolate in the bag. It's labeled chocolate. And so a human who understands how sight works and how theory of mind works should be able to realize, Sam's not going to think there's chocolate in the bag. But the large language models that pass the kind of common versions of the false belief task don't seem to pass this version. And there's a lot of examples of this in the paper of these kind of trivial modifications where a human would get what's going on and how another agent should be processing the evidence, but the large language model doesn't seem to. And so you might think they have mismatch between their signature limits, the kinds of patterns of errors they display. However, I will caution this way of reasoning a little bit by saying it's actually a really conceptually difficult thing to figure out which errors are disqualifying and which ones aren't. This is one of my favorite studies from some folks I overlapped with at Indiana when I was doing my PhD, which would suggest by similar reasoning, maybe humans can't do basic arithmetic. Okay, so what they did in this study was they varied the spacing in simple arithmetic and multiplication problems, right? That is where, say, you space out more, for example, around the plus than around the multiplication sign. And when you do that, you find people make order of operations mistakes where they'll do or sorry, you put less space around the plus, then that'll make people more likely to do the plus first when order of operations says they should do the multiplication first. Like technically, white space should be mathematically irrelevant, right? In the way you put forth a math equation. But this experiment suggests that, in fact, people are using these indirect cues, these statistical, quirks of the way problems have been presented to them in the past to get the right answer on these questions. In the same way you might worry the errors of the large language models are driven by these statistical quirks in their data set that can be manipulated in weird conditions. Gary Lupion he's a cognitive scientist who has made this case out in a variety. He has some research that appears to show people reject scaling triangles as being triangles in some cases and will insist that 798 is an odd number, right? You can get really weird errors out of humans sometimes that would seem disqualifying. So it seems like we need something more than just like they make some really howling errors in some weird situations. All right, so I promise into the chain of thought models. I'll try to do this in less than 5 or 10 minutes. So if you go to OpenAI's website, you can look at some of these new chain of thought models about which they make some pretty ambitious claims. I'll try to show you really quickly if I still have that window open. So the idea here, and here's a series of test reasoning problems that's on this web page. Um, you can go through and what they do is, all right, I'm back. I'll try one more time. Okay, just tell me if you can't hear me, but otherwise I'm going to keep going. So what they can do is they do a lot of self-prompting of themselves when they're solving these difficult reasoning problems. So, for example, you can give them a novel cipher. So here's some new code, you've never seen before. You've got to crack the code. And then, at least in the demos, you can see the self-prompting that they generate for themselves before they give you an answer. And it looks an awful lot like the internal chain of thought that a human might be doing if they were thinking in their heads in inner speech or reasoning out loud with a collaborator to try to solve this problem. You can see them exploring particular hypotheses, right, and solving the problem. saying, oh, that doesn't work. Let's try again. Ooh, that word makes sense. And you can look at this. I encourage you to look at this for lots of different problems and see how they're working. Unfortunately, OpenAI has decided to not share the internal chains of thought with us for the deployed model. So all we have to go on are their toy examples that this is how it actually works when we're using them ourselves behind the scenes. They say that's a safety concern. I'll let you decide whether that's a good argument or not. Um, but this is based on an earlier research tradition in chain of thought prompting, which suggests that simply adding a little bit of intermediate steps can increase the performance of these models. For example, we discovered early on that if you simply let's think step by step to the model before asking it for its answer, its accuracy on math problems jumps from 17% to 78%. Kind of a remarkable result. And this led to the so-called emphasis on prompt engineering as a professional specialization, maybe for philosophers, right? But now the models can prompt themselves, and they learn to do that through reinforcement learning very efficiently. Um, I've been studying this on analogy with inner speech and human cognition. Okay, so thinking about how inner speech can kind of scaffold human reasoning processes as a kind of internal tool. One easy way to see how that might work where you're actually solving the problem just by phrasing it in inner speech is counting, right? So counting is actually something that a lot of large language models have been pretty bad at. So if I ask it to count letters in a couple of difficult words or my name, it actually got the right answers on the first try. So I was a little frustrated there. But I finally found one where it got the wrong answer. Gainesville, where I live now, it's very foresty. It's sometimes called Tree City, USA. So I asked it to count the number of letters there, and it said 12 letters. That's wrong. So I could though say, please enumerate each letter independently and try again. So now it tries to build a bulleted list, right, where it numbers each letter and pairs each one with a letter. And then by counting to 11, right, purely by statistical, next token generation, it can do a bulleted list really well. That's something that occurs all over the place. And through the few shot learning, it can pair up a novel word with the numbering. And simply by putting 11 as the last letter in the list, it's in some sense solved the problem. It's made the right answer much more likely for itself to produce by producing it earlier in its own prompt. Right. So you can see how that really you are really seeing the scaffolding that produces the right answer in its mere placing this in the form of a bulleted list. Um, there's an earlier paper that talks about how some of these self-prompting methods were possible if you want to get into the details. OpenAI makes some very ambitious claims about what the internal chains of thought that we can scrutinize tell us. They say in particular, this allows us to read the mind of the model and understand its thought processes. They also make some claims about safety. I think this is all probably, serious overinterpretation, especially if we look at the psychology and philosophy of inner speech in humans. So I say read its mind, really? Does it though? Can I read your mind if you tell me what your inner speech is? I'm pretty skeptical of that position too. In fact, if you get into the philosophy of inner speech, it's been a controversial position whether we think in inner speech, in other words, that's the actual medium of our inner reasoning process, or we think with inner speech in this more scaffoldy-like way that I suggested with the counting letters. In general, there's a lot of work in this area that's quite sophisticated that argues that while inner speech can be a private, grammatically structured representational medium, that is, it is something that has representational content and it's structured in useful ways, it might be incoherent to suppose that it's both globally broadcast around the mind and self-interpreting, right? That it has the kind of exact content that we would think it does when we interpret it as language, right? So the idea here is we're reading these chains of thought in the models. We want to be very careful of the assumption that they are being processed by the model in the same way that we would process them as speakers of native language, right? That's the inference you want to be very careful of. There's a lot of background here that you could go into to see reasons for being skeptical of this move. In particular, I draw attention to this paper by Edouard Moschery, who argues you don't actually know how you think because you have access to your own inner speech. There's an argument called sententialism, which would say we think in this inner speech, in this thought-like, language-like medium, because we're aware of inner speech that tells us the kind of mechanisms of our thought, and they have these nice classical properties like compositionality and being syntactically structured with explicit relations and all this nice stuff that like Fodor and all the classical computationalists would like. And Mashri says not so fast. Um, he argues for this principle that the fact that some property is represented in your inner speech doesn't license the inference that the thought itself possesses that property, okay? Which is the kind of slip that we're doing. So imagine a green triangle, right? You know, in some sense, you're representing a green triangle, but that doesn't mean there's anything green or triangular in the thought processes that are generating the thought of the green triangle, right? And so the same worry might be going on here. You have generated a representational medium that has certain linguistic properties, but that doesn't mean that the thought processes that generated that inner set of words or that process them are themselves language-like. They could be anything. They could be all kinds of really complicated neural chaos that we've always worried about is really driving these models to begin with, right? So that's the quick version of pushing back against this view, right? We can't infer because we process these thoughts sententially or classically that the LLMs do too. In fact, might think that the holistic context dependence of self-attention, which we talked about earlier, actually speaks against this, right? If we're, dramatically changing the contextual meaning of each one of these vectors based on the self-attention operations earlier in the hierarchy, then the same time this word occurs, it can't be behaving like a classical symbol in each case, right? Because each time it occurs, its meaning has going to be been pushed subtly around in vector space to mean something slightly different. Whereas the kind of classical understanding about how this would work is that you've got these sort of abstract symbols that are functioning like, good old-fashioned AI in compositional operations that are allowing you to solve these problems through sequential rule following, right? So you might think the very fact that we know how self-attention operates to generate these internal chains of thought speaks against the idea that they're being processed in this classical way. There's a little bit of cool research here that's we might explore in between these two positions, that the chains of thought don't mean anything, and the chains of thought are giving us like this classical symbolic understanding of what's going on. Um, uh, there's a slightly less hopeful take, which is that they're chaining together islands of probability calculation that would otherwise be distant and inaccessible to the model, and that this explains their success on reasoning tasks. I'll show you an example of that right here. So there's in particular this very interesting paper by Goodman and some co-authors where they show if you allow a lot of inner self-prompting in between answering the question and being given the question and answering the question, you do in fact see a reliable increase in performance. They call this the reasoning gap. You get a reduction of error on reasoning type problems. And they have a speculation that they verify with a kind of analytical probability model of how this might work, where the idea is suppose you're asking the model a really out of distribution question. That is one that's statistically very unlike ones they've seen in the past. For example, the types of theory of mind problems that Ullman was giving the models with like a transparent plastic bag that's labeled incorrectly, right? Now, if you're just trying to estimate all the variables directly, what's in the bag, what's the label, what's the connection between the bag and the label, and so on, you're going to be less accurate on guessing those intermediate variables than if you're able to chain them together through islands where those variables did co-occur in your training history, right? So there could be places where like the label of a bag and the transparency of the bag are correlated, where what the label says and what's contained in the bag are correlated, where the position of the observer and the contents of the bag are correlated. Maybe none of those things didn't all perfectly co-occur in the past. So if you're estimating them all point-wise in this context, you're going to be unreliable. But if you can kind of use estimates of these islands of chain together probability to guess the influence of the first variable on the last one, you're going to be a lot more accurate. Okay? I can say more in the Q&A if anybody wants to hear a little bit more. There is an even more skeptical interpretation, though, which is that having a lot more self-prompting before you give an answer just gives the transformer more test time computation. Okay? So the idea is the more you let it build internal tokens between you give it the question and it gives an answer, the more it's able to kind of build richer representations through self-attention. The idea here is that one fundamental limitation of the transformer architectures we have right now is that by and large, they're not recurrent. Okay? they don't have connections from the output that go back to the input that could allow lots of internal cycling, indefinite amounts of internal cycling before it gives an answer. And one thing these self-prompting might let a transformer do is do an indirect kind of recurrence, right, through its own self-prompting to add more and more computation before it gives an answer. So this particular study by Fau, Merrill, and Bowman showed that if you just train a model to produce lots of ellipses, just dots, before it gives an answer, you also get an improvement in performance. It's not as big as the full, reinforcement trained self-prompting with text, but it is a significant increase in performance just by producing dots, right? So my thought is at least some of the performance gain you see here could be based on just more computation before you give the answer. There's other examples supporting that perspective. I'm going to stop here with just a final suggestion. And this is that if we really want to know what's going on, we can't just rely on behavioral measures, not even by scrutinizing the text. We actually need interpretability methods that try to uncover what the different intermediate steps in the activation vectors of a trained up large language model are doing. Rafael Milliere and I have a couple review papers reviewing a bunch of recent techniques on in that direction, but that's kind of a separate talk to explain how all those techniques work and justifying them on philosophy of science grounds. So I think I'll stop there and see if there are questions,
Um,
assuming my internet doesn't cut out again.
no worries. Thank you, Cameron Buckner. That was wonderful and quite thought-provoking in many ways. We can continue with questions or comments or remarks. But since this is an online talk, can you please, before asking a question, raise your hand via the button down below in the reactions section so that there won't be any chaos. Um, is there any question?
You can also just ask me to go over anything I went over too quickly.
Uh, Suzanne, please go ahead.
Hi, Cameron. Thank
Hi.
you for the talk. Yeah, it's just very interesting. I work in the AI department, and then I also am teaching at AI, but with language. So reasoning part and philosophical part and psychological part was a bit interesting and unfamiliar to me. But given the background, my question will be about language. So you said, like on page 23, around that, you said more power with something. Oh, sorry, a bit later in the pictures. I thought they are also slide numbers. Oh, can you, because one of have enough data. We don't have enough data in multilingual models, and everything we have is coming from English, etc. So we are trying to build more multilingual models, so it will be more available from the
Hmm.
ethics side and everything.
Hmm.
How about that? Because since we have very limited data from languages like Zulu, I don't know, some African languages, so we still need those data, and then we will be able to do some language models on those languages. How would it be doing reasoning on with limited amount of data?
Yeah, I think it's an open question.
Hmm.
Whether this, I don't know of studies off the top of my head. I think it's a very interesting empirical question. The only studies I know of that have looked into the computational effect of these kind of filler tokens were in kind of pure large language models in English. I mean,
Mhm.
obviously, you wouldn't want to do it on a question where the model is already achieving very high performance. So they
Yeah,
tend
I
to
think.
focus on reasoning, multi-step planning type problems, math type problems, right?
Mm, mm.
There are a couple of converging results. I kind of moved over quickly. There's another that just uses invisible pause tokens, so it doesn't even need to really output a token to the user. It could be a kind of invisible pause token, just like
Hmm.
you might say a person just kind of waits a long time before they give an answer while they're
Yeah,
giving extra thought. I
yeah.
mean, one we're always trying to figure out what do these scattered empirical results mean because things are moving so very quickly.
It
What
is.
do they tell us generally about future trends and kind of general principles of deep learning, right? And here's one emerging idea that I hear in a lot of different places is that we're learning there's different ways to scale computation for kind of scaling laws, and anticipating future gains. We've done a lot with training time computation in the
Mm.
past, right? That's where a lot of previous research in deep learning was, and certainly a lot of large language model research.
Yeah. Yeah.
And now, since O1, O3, and DeepSeek, a lot of people are now realizing, oh, test time computation is the next big source for scaling because
Mm.
they think they've started to get diminishing returns on training time scaling, right? So now we're looking at test time scaling. And I expect to see a lot more methods beyond this chain of thought prompting and search,
Mm.
where you're finding more ways to just build more computation into the test before it answers. I'm not sure if I could speak to your specific questions about applying this to, like Zulu that has a very limited data set. I think it's just a totally open empirical question.
Yeah, for sure. For sure. It's just I'm like, I sometimes ask these questions myself or to my students because they like, yeah, I teach, for example, linguistics, and they always like, okay, what I'm going to do with this information. And I said always, okay, as a as a human researcher or whoever you are, like a developer of this system, you have to know how the language work from
Right,
different point of view, or from English point of view, or from
right,
different data. And they're like, yeah, but I can teach them how to think so they can decide itself if it's doing it right or wrong.
right,
But from which point of view I should tell them, yeah, well, they don't actually do the thinking,
right.
the reasoning. So that's why it was very interesting because I was just explaining to them, and I'm still explaining it's an ongoing course. So, like, would there be any nicer things that I can tell them about? Like, okay, yes, they think, but this is how they do reasoning. So I think some of the things were very useful for me to be able to
Yeah.
build an idea. So
I think,
that's
yeah,
where
I
my
think
question
that
comes from.
to answer those questions in any particular case, we need the interpretability work I keep kind of plugging and I didn't really explain, which is you
Yeah.
need to look at how the internal representations are actually working. And that requires a different type of data analysis than any of the behavioral measures
Mm,
people are using.
yeah. Well, thank you so much. It's been very enlightening. Yeah.
I mean, what you could expect for the Zulu case, for example, they have no problem switching between languages, and they could very easily use it as a kind of, just like they treat the cipher example, right? It could be like, well, let's suppose Zulu works this way, and then it tries it out in a few different ways to see if it makes
Mm,
grammatical sense of the examples you've given it, and then
mm.
it says, no, that doesn't work. Well, let's imagine it has a different property. Suppose it works like Japanese, right? And then it tries out a few different solutions. I don't see any reason why it couldn't generate that text, but
Okay.
it still wouldn't answer this question. Is the text, what role is that text playing?
Yeah,
Right?
yeah, yeah. Yeah,
Is
yeah.
it really trying out different grammatical theories as the way it kind of looks, or is
Yeah.
it just giving more test time computation, or is it, chaining together intermediate variables, which is still a kind of interesting idea about how reasoning might actually work in human cognition, right? We could also be skeptical of how intellectualized we should think reasoning processes are in human cognition, right? And human cognition could be actually more like that kind of chaining together intermediate variables to get a more reliable estimate.
And where does, in that case, where does comparison come into place here? Because that's like you said, to do it like Japanese, then there's a lot of comparison going on there. So is that what you mean by the chain, or like?
Yeah. So what I mean, it's kind of a deflationary interpretation of how that comparison would work, right? Is that what
Mhm.
you're doing is you're like, well, I have a language that's got these two variables in it.
Yeah.
So if I do an intermediate step between through that language with these two variables, I'm going to get a better estimate of how the first variable affects, some third or
Exactly.
later one by chaining together those two intermediate properties. Does that make
Yeah.
sense?
Okay. Yeah, 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 definitely. Well, it's very interesting. Okay, if someone else is want to ask a question, I'll give
There is
myself a thank you. Yeah.
another question. Maybe we can get back to you later, Susan. Cansu Demir dropped a question to chat. Cansu, would you like to ask a question out loud or should I read it? Okay, I suppose I should read it. Thank you for your presentation. It was very interesting. My question is that you said LLMs are bad at counting and maths in general. I was wondering whether there is a particular reason for that. Is it because of the architecture that these models are using or something else?
Yeah, I mean, I think that's the general idea. This was just a empirical trend. Until the most recent models, these things just tended to be bad at really complicated multi-step math problems, especially compared to some of the other stuff that they're really good at. Um, and there's kind of obvious reasons for thinking that they're just poorly suited to math problems on the basis of, just doing operations over continuous vector spaces. The idea being that, mathematics is sort of based on the idea of exact changes in magnitude, right? Starting with counting and then bootstrapping up from there to arithmetic and multiplication and everything that comes after that. It seems like to get that off the ground, you need the idea of an exact magnitude that you can represent as being the same every time it occurs. And so if your vectors were moving around slightly in this kind of continuous space all the time, you might think they're not stable enough for exact judgments. And so what you get, people who study the cognitive science of mathematics, they often say that humans and animals tend to have two innate number-like systems. There's a subitizing system, which allows you to guess exact numbers of objects, but usually only up until like three or four. So in other words, like I throw four objects on the ground or three objects on the ground, you can very quickly see exactly it's three without having to count. And that is a kind of exact magnitude. And then we have an analog magnitude estimator system, which lets you get rough differences in amounts of stuff, but not exact, right? So that will work for large numbers. If I give you a pile of 10,000 grains of sand, you can see that's different from a pile of 7,000 grains of sand, but you'll have a very hard time telling the difference between 9,999 and 10,000, right? You probably won't see any difference, even though there is an exact difference there. And so a big question for human cognitive science of mathematics is how do we bootstrap those two systems, the subitizing system and the analog magnitude system, to get a real representation of natural number from which the rest of mathematics can kind of take off. This has been a big focus of Susan Carey's research, for example. And we'd have a similar question about large language models here, right? If they do turn out to be good at math, because their basic system has these continuous, more analog type representational properties, how do we ever get from that continuous vector space type representation system to one of mathematical properties which require this really exactness that's the same in all cases where it occurs? I hope that answers the general gist of the question.
Thank you. Um, Sarjan, please go ahead.
You hear me well? Okay.
Yeah,
Yes.
Thank you so much for your very informative talk. I really enjoyed it. Towards the end, you mentioned that OpenAI's claims are too ambitious, and coming from OpenAI, I 100% agree with you on that. This is not recorded, I hope. I also found your critique of performance-based reasoning metrics very compelling, particularly the concerns about the reliability that people have been writing about and whether they truly capture what we want them to capture. This is also another question, I think. But I completely agree that these metrics can be problematic, and I agree that the performance-based evaluations might not be the best way to assess reasoning in large language models. That said, perhaps the naive question here could be something like if performance-based metrics are flawed, which I agree, as I said, what alternatives should we consider, especially
yeah,
given the chain of thought reasoning is introduced to make the model's reasoning process more interpretable, which we
right,
call as explainable AI, to see
right,
what's going on there. I still, because
right,
LLMs are like black boxes. I
right.
still see value in this approach, I think. However, I struggle to determine the best way, maybe, or one of the best ways
Yeah,
to assess reasoning capabilities,
yeah.
especially in the integration of word knowledge, because people have been, especially in MIT, Evelina Fedorenko and her team have been writing a lot about whether LLMs can successfully have this world knowledge integration and all that stuff. And generally, the answer in the literature is no.
Right.
And my second question, or maybe like a comment, is like, probably like Piandodosi's paper recently arguing that LLMs refute Chomsky's innateness hypothesis. And this paper has sparked significant amount of discussion on LinkBuzz and several platforms among linguists and psychologists, because basically his claim is that, okay, we have LLMs, they produce language, and basically Chomsky's innateness hypothesis is totally wrong, something
Yeah,
like
I
this.
know
And
the
the
paper.
title is
Yeah.
Refute Chomsky's Innateness, I think, which is a big title. And I'd love to hear your take on that debate if you have.
Sure. Let me try to remember the first one first. So what do we do instead if you share my skepticism of performance-based metrics? Well, like I plugged at the end, I'm working on understanding interventionist techniques. You probably know that Anthropic has been working on a lot of these techniques. That's one approach. There's a bunch of other people in the area. And Rafael Milliere and I have a couple of review papers that are available as preprints for sure, if not already published, that review a lot of these techniques and give our sort of take on the situation. That's at least where I'm putting my chips right now. As it stands with being able to scrutinize the inner chain of thoughts, I don't think it's nothing, right? So I don't want to give the impression that I think being able to see the internal text that they're generating for themselves doesn't give us any evidence about what's going on. I'm just arguing that we can't take for granted that it's processing these sentences in the same way that we would as full, compositional understanders of natural language. So if you're a psychologist and you have access to so-called protocol analysis of humans while they're solving problems, this is where you ask them to speak aloud while they're solving a problem. I think it has the same epistemic status as that does for humans, right? Where you don't know necessarily what role the words they're producing or playing, but it definitely does give you information about, say, what the person is attending to at the time, right? And so I think you have to go from there. Say, okay, so if I know they're attending to this word and probably bits of their statistical training set that this word is related to, I now need to do interpretability work where I'm actually probing the internal workings of the system, the activation weights that were behind its production of that word, or its ranking for that chain of thought branch, or whatever, to see is it actually playing the role that I think it might be playing based on its performance. I mean, there's all kinds of background reasons from earlier XAI techniques to be worried about this. You probably know some of Cynthia Rudin's work, for example, criticizing salience mapping in earlier deep convolutional neural networks, right? Where, sure, you can find a nice salience mapping technique where you do a heat map and you light up parts of the input image that seem to be causally particularly responsible for producing the verdict that the system gave on that particular trial. But that doesn't mean you know how it's representing that feature, right? So she has these examples, right, where you show a picture of a dog and it lights up certain images on the snout and so on. And it says, oh, that's the evidence it's using to make its classification that this is a Siberian Husky. But it will light up, almost the exact same pixels for other classifications. Like it's a flute was one of the other examples, lights up almost the same pixels. So you don't really know how it's construing those properties that in some sense it's activated and are being manipulated. In order to figure that out, you have to do interpretability work. I can jump ahead. Am I still sharing my screen?
Yes.
Oh, I can jump ahead a little bit just to plug some papers. So this is the paper I have with Raphael I mentioned. It's earlier back. Yeah, I would look at a lot of Atticus Geiger's work. This has kind of been the focus of his. Maybe you know him. I don't know if you're in the Bay Area or not, but it has been the focus of his dissertation and a bunch of surrounding papers at Stanford. And he has a whole theoretical approach to try to build causal models of how these models might be working, and then systematically verify whether the causal models are accurate using interventionist interpretability techniques, where you actually probe the internal workings of the system, you move the activation vectors around in ways that are driven by your hypothesis, and see whether the the outputs of the model change in a systematic way that you would predict if your original hypothesis was right. Now, what was the second question? Oh, yeah, Piantadossi on Chomsky being entirely wrong. Yeah, so I mean, Piantadossi knows how to drum up a controversy. The I mean, the response that everybody gives to that paper is, yeah, okay, maybe some of the Chomskyan linguists have made very grandiose claims that statistical methods would never be able to produce the kind of really highly accurate grammatical output that we see in large language models. So those extreme versions of the view are wrong. But then there's also a lot more moderate versions of the view. Chomsky himself famously way dialed back his nativism mid-career. And they always, all versions of the view emphasize poverty of the stimulus. And so what you really need to focus on if you want to make these really strong conclusions that Piantadosi is making, that Chomsky's linguistics is entirely wrong, is you need to be showing that you can get that level of grammaticality from human-like training sets. There are people trying to do this, right? So like the baby LM challenge, which has been going now for a few years, that's exactly what I would follow if I really wanted to figure out the right answer to this empirical question is given, ecologically valid human-like training sets, can these models achieve human level grammaticality judgments, or do they still fall way short and they need like orders of magnitude more exposure? I think things are looking kind of promising in the baby LM challenge, but it's not like an overwhelming victory yet.
Um, Thanks. There's another question in the chat by, I hope I'm not going to pronounce it wrong, Martin Gutierrez Bernardos. Um, Thank you for the talk. My question is again on language. You said that LLMs use vector semantics and embeddings, but can LLM benefit from using another kind of semantics, maybe some that are directed to natural language, such as inquisitive semantics or situational semantics?
Yeah, that's a super interesting question. I mean, if you look at the original Transformer paper's citations today, I think it's gotten something like 170,000 citations in the last 5 years. So I hesitate to say anything with conviction about what's in the literature, right? I would suspect that any idea you can form that's half coherent, somebody is actually trying to do right now, right? So trying to meld situation semantics together with large language model and vector semantics. Maybe nobody's tried that yet, but maybe somebody's trying it right now. I really have no idea. I think the sky's the limit, right? Obvious things you could do so-called tool former architectures, right? So where you give a transformer a little bit of access to some kind of a programming library, maybe with a little explicit representational structure, right? And you could have it learn adaptively to make calls to that programming library. So maybe you find some way to code up situation semantics. I've worked with answer set semantics in my old GoFi career, 20 years ago. And you could easily imagine, and people are actually doing it, where you use the machine learning just to generate certain formal structures that you can then plug into an interpreter where you do some classical processing off to the side, and it figures out what are the implications of those formal structures that the vector semantics-based approach has learned to generate in its standard statistical training methods. And then you can feed the results back into the transformer for more computation later on. I don't see any reason you couldn't do that with situation semantics or any other formal apparatus you're interested in investigating. I mean, some of the coolest results, some of you at least are going to know the Sparks of General Intelligence paper that was done with a really early version of GPT-4 by some team at Microsoft that was kind of investigating a non-nerf version of it privately. Some of the coolest results there for me were in a kind of tool former uh, thing with multimodal architectures, right? So there were these examples where they queried its ability to make novel compositional images like of a unicorn. And if you ask it to kind of generate those pictures directly from its own, if you gave it a visual transformer or whatever, they would be kind of incoherent, often compositionally, in the ways that early versions of image generating deep learning programs were. But if instead you have it generate LIX code, which is a visual markup code for generating figures in LaTeX documents, then it can learn to compose the instructions in the visual markup language, right, as kind of like programming. And then you just use the interpreter to build the actual diagram. And if you do it that way, it gets much more compositionally coherent results than if you have it try to generate the images directly from like a visual transformer without going through a visual markup language. And so, I would expect there's all kinds of knock-on benefits for whatever other kind of formal semantics you're interested in if you gave it that kind of access to a interpreter or formal scaffolding.
Thank you again. I see Buse has asked something. Can we have the slides? Can we share the slides with the audience?
Sure.
Great. Thank you again. So, Is there any other question? If not, as the last question, maybe Suzanne would like to ask something. I remember uh, she was going to ask another one. Suzanne, would you like to ask another question? Okay.
Sorry, no, I don't have any further questions. Thank you.
Okay.
Thank you. That was clear.
Uh, okay, so maybe we can say goodbye. It has almost been 1.5 hours, so I want to thank again. I want to thank again Dr. Cameron Buckner for this quite uh, satisfactory talk. Um, uh, I had lots of ideas, so thank you again for accepting our invitation. And also, I would like to thank you all for joining in today with us. And yeah, thank you and goodbye. Have a nice day and or have a nice evening.
Yeah, thanks for the questions.
Yeah. Thank you. Good evening.